Hey everyone. So today we're going to be talking about L'Hopital's rule. That's section 5.3. And L'Hopital's rule is very, very interesting. I find that it gets a lot of unnecessary hate, probably just because the name makes it sound like it's going to be really hard. L'Hopital's. Um, but the L'Hopital's rule will let us find the limit of indeterminates. So that was when we had 0 over 0 or infinity over infinity. So this is going to be a limit section again. So let's get started. So before we get started with L'Hopital's, it's probably worth looking at limits. It's been a while since we've done anything with them. So here we've got four examples. We've got y equals x squared, y equals 1 over x, and y equals 1 over x squared. And the reason I picked these ones are a lot of the functions that we're going to deal with will look like this. If we are looking at a polynomial of odd degree, it will kind of resemble y equals x. It might be a little more wiggly, but it's going to start negative and end positive. When we deal with x squared, or polynomials with even degrees, we're going to get like a parabola-like shape. We're going to start positive and end positive, or start negative and end negative, probably just with a little bit of wiggle in the middle. 1 over x, this is going to be similar to 1 over something to an odd degree. And 1 over x squared is going to be similar to 1 over something to the even degree. So these four functions are going to resemble a lot of the functions that we may run into. So if any of this is confusing, you may want to go back to chapter 3 to just review some limits. But these are four of the primary ones that we're going to be looking at today. So here wants us to evaluate each limit. So we've got the limit as x approaches 3 from the right of 7 over x minus 3 to the fifth. So if you look at our last slide, this is going to be like the problem 1 over x. It's a number over an odd degree polynomial. And they're saying that it's 3 from the right, so that means it's something slightly bigger than 3. So how I see this is it's really like 7 over positive 0, if that makes any sense. It's really close to 0, but it's a positive number. And if you divide by 0, you're really getting something huge, something like infinity. And it's going to be positive infinity because 7 is positive and our denominator is positive. So I would say that this limit goes to infinity. Very much like the problem on the last slide, the 1 over x. For b, the limit as x approaches -4 of 6 over x plus 4 to the sixth. So this will behave like our 1 over x squared function. Now remember, being an even power in the numerator makes it so that, or not in the numerator, in the denominator, makes it so that everything on the inside is going to be even. Even if we were plugging numbers for x and get negatives, once we raise it to the sixth power, it's going to be a positive. So this is going to be 6 over positive 0, which is infinity. For c, we're looking at the limit as x goes to negative infinity of 3 over x plus 2 cubed. So this is going to, again, look like our first function because we have an odd degree. 3 is positive. And if we're going to negative infinity and we're cubing it, we're still negative. So this is negative infinity. And dividing by infinity, if you have 3 and you're breaking it into infinitely many parts, those parts would all be 0. So this would be 0. And then d, 5x to the fourth as x goes to infinity. I mean, just imagine plugging in a really, 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 really big number, raising it to the fourth power and multiplying by 5, you're going to get infinity. A quick review of limits using exponentials and logarithms. Here we have e to the x, e to the negative x, and ln of x. So when we have something to a positive power, like e to the x, we get this exponential curve that's pretty famous. If it's e to the negative x, it gets reflected over the y-axis. And then when we're looking at ln of x, or really any logarithm, it always follows this similar curve here. So take a look at these. If they don't make sense, it might be worth looking back at chapter 3, but these are also some limits that we may have come up later in this section that we're going to use L'Hopital's rule on. So it says evaluate each limit. So the limit as x approaches negative infinity of 2e to the negative 6x. So this is going to be similar to e to the negative x, and as x approaches negative infinity, we are going to get positive infinity. The reason being is this is going to be 2e, negative 6 times negative infinity is like 6 times infinity, and e to the infinity is infinity. For b, the limit as x approaches negative infinity of 3e to the 2x. If we were to plug in, we're going to get 3e to the negative 2 infinity, and that's going to look similar to the first function on the last slide, which was e to the x. And as x went to negative infinity, this went to 0. For c, the limit as x approaches negative 4 from the right of ln of x plus 4. And it has to be from the right because the ln of 0 doesn't truly exist. So we got to take a limit as it approaches 4 from the right. And if you take a look at that, the limit as we approach the ln of 0 is going to be negative infinity. And then as x approaches infinity of ln of x minus 10, well, this is really the ln of infinity, which is infinity. On this slide here, we're going to start talking about L'Hopital's and when we would need to use L'Hopital's. So they say, recall that if we've got the limit as x approaches c of f of x over g of x is a 0 over 0 indeterminate form if f of x is approaching 0 at c and g of x is approaching 0 at c, because this would give us a 0 over 0. So there's two examples that we can take a look at. This first one would be one that we should be familiar with. The limit as x approaches 2 of x squared minus 4 over x minus 2. If we plug in 2, we're going to get 0 over 0, no surprise. But we could go ahead and factor this out and see if something cancels. X minus 2 times x plus 2 over x minus 2. The x minus 2's will cancel. So we get the limit as x approaches 2 of x plus 2, which is 4. So this first one, even though it appeared to be a 0 over 0 at first, we could do some cancellation and figure out that this is going to have a limit of 4. But now let's take a look at the second one. The limit as x approaches 1 of e to the x minus e over x minus 1. If I plug in 1, I'm going to get e minus e, which is 0, and 1 minus 1, which is 0. It's a 0 over 0, but nothing cancels. And this is where L'Hopital's rule is going to come in, and we'll see that on our next slide. So theorem 1 is L'Hopital's rule for 0 over 0 indeterminates. So this rule will grow throughout this section, but right now if we have a 0 over 0, it says that the limit as x approaches c of f of x over g of x is the limit as x approaches c of f prime of x over g prime of x. And again, this is only when we are getting a 0 over 0. What L'Hopital's rule is saying is take the derivative of the top and take the derivative of the bottom and evaluate the limit again. So let's solve that problem using L'Hopital's. So this is the one from 2 slides ago. And if we plug in 1, we're going to get 0 over 0. So remember, L'Hopital's is only going to work if we have an indeterminate. If the limit can be solved by plugging in, we have to do it that way. L'Hopital's won't help us. But here, we do get a 0 over 0. So it says take the derivative of the top and the derivative of the bottom and plug in again. So I usually do like an arrow with like an LH or something, just so people know I'm applying L'Hopital's rule here. So what is the derivative of e to the x minus e? Well, the derivative of e to the x is e to the x. And the derivative of e is 0 because e is a constant, divided by the derivative of x, which is 1, minus the derivative of 1, which is 0 because 1's a constant. So let's take this limit again. E to the 1 is e over 1, which is e. So this limit right here is e. And this could only be solved using L'Hopital's rule. There was no way to do a cancellation. Example 2, it says evaluate the limit as x approaches 4 of e to the x minus e to the 4 over x minus 4. So if I plug in 4, I'm going to get a 0 over 0. It's e to the 4 minus e to the 4 over 4 minus 4, so that's 0 over 0. So I need to use a L'Hopital's. So indicating that I'm using L'Hopital's. So this is the limit as x approaches 4 of e to the x over 1. And if I plug in here, I'm going to get e to the 4. So that is my limit. Example 3, the limit as x approaches 0 of the ln of 1 plus x squared divided by x over 4. So if I plug in 0, I'm going to get the ln of 1 over 0, and the ln of 1 is 0. So this is a 0 over 0 indeterminate. So I need to take the derivative of the top and the bottom to use L'Hopital's rule. So this is the limit as x approaches 0. Now, the ln of 1 over x squared, we are going to have to use a chain rule. So this is going to be 1 over 1 plus x squared times the derivative of the top, which is 2x, all over the bottom, which we're going to get 4x cubed. Okay, so does anything cancel out? Well, there is an x in the numerator, and there is an x cubed in the denominator. So I can have this x, and this power would become a square. And let's see, does that help us at all here? We would be looking at the limit as x approaches 0 of 1 over 1 plus x squared times 2, all over 4x squared. Now, this can reduce. If I turn the 4x squared into 4x squared over 1, a fraction over a fraction means flip and multiply. So my numerator, I'm going to simplify this as 2 over 1 plus x squared, and I've dropped my limit. I need that limit as x approaches 0, times flip and multiply, 1 over 4x squared, and this will give me 2 over 1 plus x squared times 4x squared. And I forgot my limit again. So let's evaluate that limit. If I plug in 0, I'm not getting 0 over 0. I'm getting 2 over 1 times 0. That's 2 over 0, and that would be infinity. So this is an infinite limit. So number 4, the limit as x approaches 1 of ln x divided by x. Now, if you're thinking that we need to apply L'Hopital's rule, you're making the rookie mistake here. This is the number one mistake I see made with L'Hopital's. L'Hopital's only works if we have an indeterminate. We first need to see if L'Hopital's is needed here. So let's plug in 1. The ln of 1 is 0 over 1. This is 0. No L'Hopital's rule needed. So in fact, if you use L'Hopital's here, you're actually going to get the wrong answer. I believe if you use L'Hopital's here, you're going to get 1. And the answer should be 0. So remember, check to make sure you're getting an indeterminate before you apply L'Hopital's rule. So here in example 5, it's giving you a heads up that sometimes you're going to have to use L'Hopital's rule more than once to evaluate a limit. In fact, it's pretty common. So let's plug in 0 and see what happens. I get 0 squared over 1 minus 0. That's going to be a 0 over 0. So let's apply a L'Hopital's rule to it. The numerator is going to be 2x, and the denominator will be e to the x minus 1. And this is the limit as x approaches 0. If I plug in 0 again, I'm going to get 0 over 0, or 0 over 1 minus 1, which is 0 over 0. So I'm going to use L'Hopital's again. So this will be the limit as x approaches 0 of 2 over e to the x And this is something we can evaluate. This is going to be 2 over 1, which is 2. So my limit is 2. So just because we have to use L'Hopital's more than once doesn't necessarily mean the problem is going to be difficult. So theorem 2, also about applying L'Hopital's. So it says that if you've got a 0 over 0 indeterminate, and you're using one-sided limits, this still works. So we didn't really talk about, well, what happens if we have one-sided limits or we're using infinities and negative infinities. But the answer is L'Hopital's will still work. It's still derivative of the top divided by the derivative of the bottom, take the limit again. Which is kind of nice. It didn't really change, it just got better. It's more powerful now, it can handle more things. So for number 6, it says evaluate the limit as x approaches 1 from the right of ln of 1 divided by 1 minus 1 squared. So if you plug in 1 here, you're going to get 0 over 0 squared. So clearly this is a 0 over 0. So we're going to use L'Hopital's. And the derivative of ln x is 1 over x. And don't forget that we are taking the limit as x approaches 1 from the right. And in the denominator, this is a chain rule if you don't want to multiply it out. So this is going to be 2 times x minus 1. The derivative of the inside is just 1. So this is 1 over x, don't forget my limit, divided by 2x minus 2. So if I plug 1 into here, in the numerator I'm going to get 1, and in the denominator I'm going to get 0. And we have to kind of determine, is this a positive 0 or a negative 0? I'm saying that it's 1 from the right, meaning I'm plugging in something slightly bigger than 1. So if I'm plugging in something slightly bigger than 1 in the denominator, it's going to be something that's slightly bigger than 2 minus 2. So this is really a positive. So I'm going to get an infinite limit here. Example 7 says the limit as x approaches infinity of ln of 1 plus e to the negative x divided by e to the negative x. So what is this really? Okay, so this would be the ln of 1 plus e to the negative infinity is 0 over 0. So this is going to be a 0 over 0. So I have to use L'Hopital's. So let's use L'Hopital's. I was just confirming that this is a L'Hopital's problem because textbooks love to trick people. So if I take the derivative of the numerator, I'm still doing limit as x goes to infinity. I'm going to get 1 over 1 plus e to the negative x times the derivative of the inside, which is going to be negative e to the negative x, divided by negative e to the negative x. So here, before I'm plugging in, I actually have a cancellation right away. Boom. And this will be the limit as x approaches infinity of 1 over 1 plus e to the negative x. If I plug in infinity, I'm going to get 1 divided by 1 plus 0, which is 1. So my final answer is 1. And now L'Hopital's rule form 3 or version 3. It says that version 1 and version 2 were for 0 over 0s. But what happens if we get an infinity over infinity or a negative infinity over negative infinity? Or really an infinity over negative infinity, that also is fine. What's going to happen is we will still be able to use L'Hopital's rule. That will still be an indeterminate, and L'Hopital's will apply the exact same way. The derivative of the top divided by the derivative of the bottom, take the limit again. So let's see an example of that. So the limit as x approaches infinity of ln of x over x squared. So if I plug in infinity to both the numerator and the denominator, I'm getting infinity over infinity. So that's going to be a L'Hopital's rule. L'Hopital. So the derivative of the top, oh, don't let me forget my limit. I'm notorious for that. The derivative of ln x is 1 over x. And the derivative of x squared is 2x. So if I plug in infinity here, I'm going to get 0 over infinity, which is actually going to be 0. 0 divided by anything is going to be 0. The only time that we would have to check something is if I got a 0 over 0, but my final answer is going to be 0. And if you're not sure, you could manipulate this as 1 over 2x squared. Take this limit again, and you're going to get 0. Yeah, that's just if you weren't sure what to do with a 0 over infinity. We can verify that in another way. So some closing thoughts on L'Hopital's. I like to think that L'Hopital's isn't too bad. It helps us revisit limits. So maybe the difficult part there is that it's been a while and we do need to remember our limits. But other than that, I mean, it's really derivative of the top divided by the derivative of the bottom, take the limit again, but it only works if we have an indeterminate. That's probably the number one mistake I see. People forget that you have to see if it's an indeterminate first. And I think that happens because we kind of get tunnel visioned. If you do 3 or 4 L'Hopital problems in a row, you just assume that the next problem is going to be a L'Hopital's because that's what we've been doing. And that's where you have to be careful because teachers love to throw in something where L'Hopital's won't work. Textbooks do that to you all the time. First, check if you can just plug in. Don't work harder than you have to. The second thing that I see people complain about with L'Hopital's is they will remember that we did a section called L'Hopital's. They'll remember that it was a weird name that sounded like El Hospital, but they won't remember what it is. So they just assume that it's hard. But don't let anyone tell you that L'Hopital's is bad. It's really, really not too tough. Derivative of the top, derivative of the bottom, take the limit again. But of course, only if you had an indeterminate to begin with. So other than that, the homework should be posted. And if you have any questions, feel free to reach out.